I'm presenting. Is it seen?
Yeah.
Yeah. Okay. All right. Do we start now? Okay. Are we waiting for some more time?
Yeah, we can start.
We can start. All right. Right. So, hello everyone. This is part one of the three-talk series on stellar astrophysics. This part is going to be on stellar structure. All right. So let's go on. When I first say stellar, what's the first thing that comes into your mind? What do you think of when I say stellar? Anyone?
The medium of the space.
Okay. Okay. Go on. Anyone else?
I think something related to stars and the universe.
Yep, that's pretty much it. So, so stellar in specific has got to refer to stars. Stellar in Latin is star. So, well, I'm pretty sure at some point all of us would have definitely heard of Twinkle Twinkle Little Star. But do we actually wonder what a star is? So, what is a star? So, a star is any massive self-luminous. One second, I think I'll. Yeah. So star is any massive self-luminous celestial body of gas that shines by radiation derived from its own internal energy sources. So the keywords here are self-luminous because massive celestial body can be anything else. Anything in the sky that has quite large mass can be a massive celestial body. But the keyword of what defines a star is that it is self-luminous. That is, it gives out its own energy, and it shines by radiation derived from its own internal energy sources. So I think we're all quite aware that stars are really, really far from our eyes, and only a few stars of how many of a millions are there are what are visible to us. And we can also see that they actually quite don't look the same. Now, if you look at two stars in the sky, they're likely to not look the same. They might look different. They might differ in brightness. Now, why does that happen? So, why do stars vary in brightness? One thing is, of course, that if you have two identical stars and you keep one far, it's obvious that they'll definitely look very different. And another can be because of a difference in their intrinsic brightness, in the sense of their own brightness is actually very different because their age, the stage of evolution, their mass, and there are a lot of things that can actually change a star's brightness itself as a body, irrespective of the distance, even if they're kept at the same distance from us. Before we go ahead into defining and actually making a sort of prediction on how a star should look like, we make a few assumptions, which just makes our lives easier. A star emits a spectrum of radiation. This is what we get from data. This spectrum is a continuum at all wavelengths, and this is if you actually plot all these wavelengths, they're very similar to the black body graph that we find. So what we can assume is that a star is considered a black body with respect to its emission. It's I think that's quite clear. It's like the wavelengths it emits are very similar to that of a black body, so a star is a black body. That's sort of what the assumption is. A second assumption we make is that any single star you consider, you pick one star and it's considered to be isolated. In the sense, its processes, its evolution, its future does not depend on any of the other bodies or stars. It can be anything, any of the other bodies that are around it. So its evolution is dependent only on whatever happens inside it. That is its own internal processes. That's another assumption. Although this assumption is kind of overridden when it comes to very large binary stars, which are like two stars revolving around each other and stuff. But then that's for later. Basically, a lot of stars do obey this, so that's okay. Another assumption is that a star is spherically symmetric. So I'm pretty sure all of us would have learned spherical coordinates at some point. So what happens when something is spherically symmetric is that most its properties are sort of confined only to one coordinate, which is the radius. Everything else is symmetric with respect to each other, with respect to whatever other angles or whatever we take. So in the end, whatever properties we measure are going to vary upon one coordinate, and we'll consider that the radius, the r coordinate, and that makes the calculations a lot more easier. And another assumption is that a star is static instantaneously. That is, it's not expanding or collapsing at a given instant of time. So when you're looking at the star, it's just there, it just exists. So that's one thing. And the next one is that a star's composition. A star is mainly it's composed of hydrogen and helium, and all the other elements, other heavier than helium, are just considered metals because their contribution to the whole mass is quite less, and it doesn't really make a difference if whatever you consider it as. So they're all considered metals. So these are a few assumptions we make before we proceed. Right. So we have some idea on, okay, what are the, we sort of defined a few things, assumed a few things. Now what after the assumptions? We try to build what is a stellar structure model with whatever assumptions we have and whatever data we might get. This model, why do we make this? It's because just to somehow figure out, or at least intuitively understand, what the internal structure of a star is. And knowing the structure, we can predict how much energy it radiates out, what color it is, and what happens to it as it ages. All this can be, to a certain extent, predicted with what models we can make. Right. So to build a stellar structure model, we need to know a few parameters. Anyone has any idea what, if I have to define a structure of something, what are the quantities I might need to consider? Of course, this radius, because that's what, this is like the independent variable. We don't really have to worry about what this depends on, because this is like the coordinate that defines everything else here. What else do you think is important when we define when we're trying to build a structure of something, when you're trying to explain a structure of something? Sorry?
The mass of the star.
Perfect. Yes, there's mass.
Volume.
All right, there's volume. Go on. So there's volume. So there's mass and volume. So there's density. Now there's volume. So there's pressure. Now there's volume and pressure. So there's temperature. There's temperature. Nice. Okay. Nice. All right. There's luminosity. So yeah. So what happens is, all right, composition. All right. Okay, that's good. I'm gonna keep that for the end. Composition. Okay. Anything else? Any consequence of whatever we've seen here?
Surface temperature.
Okay, that comes under here. Okay, all right. So we need to note something pretty important here. It's just that all of these are going to be functions of the radius. Mass is going to be a function of the radius. Volume, okay, as of now, we can consider it to be a function of the radius. Density is also this is one thing important. Density is not constant throughout. It is a function of the radius. And then there's pressure, which is again a function of the radius, and so is temperature and luminosity. So if you plug in the final radius, like the largest, the entire radius of the star, the final observable, huge, large radius of the star, whatever we get with respect to temperature, that is what you call the surface temperature, because that's what you see at the top at R. And this is pretty similar to what you would consider to be the effective temperature of the star. That is approximate. It's an approximate. And then there's surface luminosity. We'll define luminosity as small, lowercase r. We'll take surface luminosity to be the uppercase r. All right, but yeah, that's okay. So this is luminosity, and this is luminosity at r. Right, and of course, like when mass at r is going to be 1 capital M, because this is pretty much it. This is all like the main variables we're going to use as we try building the equations, like getting through the equations.
Do we consider entropy?
Entropy? That's an interesting question. I honestly don't know. In fact, why do you think we would consider entropy? Entropy is disorder. I'll just put it up here. least as far as what I have learned so far, we haven't considered entropy as such. But we do consider a lot of processes that happen which will explain what disorder, how disorder will change within the star. So I guess getting the entropy term somewhere there can actually, I think all that accounts for how much of whatever processes would happen inside. But then thank you for pointing this out. I think I'll look into it.
This stellar structure is for all stars, right? So
This is a yes. This is a very general structure.
So if we are pointing out a neutron star or something like that, we'll need entropy to define it, right?
Yes, that is what is going to happen. Right now, remember one of the assumptions is like it's static at this moment. We consider static, so it's not the measure for. Okay, so how do I explain this? All right. So at the moment it's static, so we build a model. What happens if I change the balance of whatever exists right now? What kind of disorder is that going to result in? Is what is going to define what process it will undergo next, and all that will come into stellar evolution. And stellar evolution is after stellar structure. So at the moment, we would be considering only a static star, at least to build the model in the beginning. Does that make sense?
Yeah, thank you.
Harini,
Yes,
sorry
yes.
to interrupt
No
here.
problem.
Yeah,
problem.
participants, please ask your doubts towards the end. Let the
Alright.
meeting,
Yeah.
whatever question Harini asks, you can answer that, sure, for sure. But like in case of any specific doubts, just write them out or just type them in the chat box, and that will be answered by the speaker at the end.
That makes sense. Yep, we can do that. All right. As we proceed, right. So mass conservation, quite evident in the name itself. Mass is conserved. So star is basically considered to be a collection of multiple spherical shells, one on top of each other, of each shell of mass dm, and this is r, thickness is dr. I mean, this is pretty similar to what we do in normal mechanics of what we've done so far. I think this equation actually makes sense because dm, the mass of this shell, is going to be the mass of the sphere until r plus dr minus the mass of the sphere at r. That makes sense, right? This much. So from that, what we can say is this is quite intuitive. What we would do is that you take the area of this much, multiply that by dr, and multiply that with the density. Now that should give you the dm. Like dm is going to be 4 pi r square dr times rho. But rho happens to be a function of r. That's the only difference. Now this is as simple as this. This is literally the first equation of stellar structure, and it's the equation of mass conservation. I hope this is clear. Moving on. Right, we have something known as a hydrostatic equilibrium. So, well, a star exists. So it is there. It is, which means that it is not exploding under its own gas pressure. At the same time, it's not at the moment collapsing under its own gravity. So, given we're watching a star, even though it's evolving, even though processes are happening, those processes are too slow. So at the instant of whatever we're seeing right now, it is static enough for us to say that there is a pretty well developed equilibrium between the gravitational attraction on the star, on each layer of the star, and the gas pressure, which sort of equalizes, like it kind of is in equilibrium with the gravitational force, so the star doesn't collapse into itself. So what's quite nice here is that okay, again, the same thing that we said is this is one layer in a star. We'll take the star to be quite larger. Ignore my horrible drawing, please. But let's say this thing, on this layer, you have the gravitational pull inside. You have the gas pressure outside, and you also have like this pressure from whatever is the rest of the star that's inside. So basically there's like two forces pulling inside and one force pushing outside. So what you can say is, okay, also before that, When I say pressure, it's easily assumed that it's always the radiation pressure. But in stars, actually, the gas pressure overrides the radiation pressure by almost the order of 10 power 4. So we assume, at this case at least, to the gas pressure to be the majority of whatever pressure we're considering. Radiation pressure will come in later, so we're not ignoring it, definitely not ignoring it. It's quite significant. But this radius to be r, and this is actually a shell of thickness dr. The drawing is bad, but this is a shell of thickness dr. So what we can quite nicely say is that the pressure, one second, I'm sorry, we can put it in terms of force actually. Let's just put it in terms of force. We can say that this pressure at r times 4 pi r square minus pressure at r plus dr. Now this is where it's a bad drawing, I'm sorry, but yeah, I hope this is clear. Minus fg, where fg is gravitational force, 0. Now this is inside, this is inward, so it's the negative signs, and this is like the r plus dr force is whatever is like that is the force, the pressure of the whatever is outside this layer on the layer. I hope you understand that. And this should technically have been r plus dr whole square, but then the dr term is like really small. I'm sorry to the math people out there, but yeah, so we ignore that. We just consider this to be just normal 4 pi r square. So this is quite a good equilibrium equation, and you can quite clearly see that we'll just we will make a few changes to this equation. What we'll say is, this is exactly what I had written. This is just the gravitational force, normal gm dm.
Harini, hello. Harini, you are not audible in case if you can hear me.
Hello, people. I'm very sorry.
Yeah.
Internet randomly decided to die down. Can anyone tell me when I left the meet?
I guess like in the derivation wala page in the top right corner when you wrote that you were explaining about
DM.
DM you wrote, and after that screen got still.
Which DM? I think I wrote a lot of DMs. One
I
second.
mean, you can share the screen, then I can.
Somewhere here? Is this where I'd stop? Or
Yeah,
even before that? Like
I guess here only. No, here only.
I ended up losing all the lecture, whatever notes I'd done. But okay, all right. Is this where it stopped?
Yes, here only.
Okay, yeah.
Okay, you can continue.
Right. So I think we'll have to go over this again. So was I there when how the pressure equalizes the gravity was done? Anyone?
I guess, yeah.
You guess, yeah. Okay.
I mean, yeah.
Yes or no?
Yes.
All right. Okay. So what we see here is, okay, I'll just go over briefly again. This is the pressure that's pushing outwards. This is the pressure that's pulling inwards. This is the gravitational force that's also pulling inwards. From our first equation, we can, oops, oh my God. Okay, one second. From our first equation, we can say that dm was the same as 4 pi r square rho dr. We just plug that in, and a little more rearrangement gets us to this, where here we can say that the dp by dr equals minus g rho. This is the second equation of stellar structure. This is the equation of hydrostatic equilibrium. And in this equation, what is the most prominent is that the pressure, okay, by the way, this is g. Gm by r square, this is g as an acceleration due to gravity. So g is positive, rho is always positive. So dp by dr is going to be negative because it's negative of a positive term. Now, what the takeaway is that the pressure gradient as you go from the center to the surface is going to decrease. In the sense, the pressure of the star itself is going to decrease when you go from the center to the surface. This is the takeaway of this equation. Let's proceed. Going next, we have. All right, so we talked about going from the pressure to this pressure at the center to the surface. So we have a star. Please don't mind my drawing again. We have the center and we have the surface. So we have the pressure at surface. Let's take capital R. This is actually 0 because there's nothing on top that's pushing it down. And by the surface, I mean just above R, like R and like an instant above. So there's nothing that's actually even pushing at it. I mean, it's kind of weird to think of it intuitively, but this is what it means. If this is 0, then what should be the pressure at the center? This is something which we can actually calculate pretty nicely. Just integrate the equation we got. We got dp by dr is equal to gm by r square minus gm by r square rho, right? If we integrate on both sides with like, okay, dp equals minus gm by r square. You integrate both sides from 0 to r. You can even write that as center to surface. There is a problem here. I would want someone to unmute. Can you think of what the problem is? Why we cannot compute this?
Because of the density itself changing.
Exactly, precisely. So that's kind of why we cannot really compute this. So what we can do at this stage is try and express everything in terms of mass. So dp by dm, you try to see how pressure changes with mass, convert the mass to the independent variable. Now what happens is, you can just write this as dp by dm. This makes sense, right? We could do this, right? We know this from the first equation. We know this from the second equation. So we could try and figure this out. So what we get here is basically this minus gm by the rho actually gets cancelled. If you can see gm by r square rho, and then here you have 4 pi r square rho. So that cancels out, and this is what we end in. So we can do this. We can now do this. There's another problem again. Anyone?
Mass is also changing with radius, no?
Yes, mass is changing with radius, but right now we made mass the independent variable, right? We don't know how the radius changes with mass.
Radius,
Yeah.
radius is changing. I mean, it's not
Exactly. And we don't know how it's changing again. We don't know the relation. We can't do anything about this. But we want to find the pressure at the center. So what we can do is, I hope I have an empty slide next. Yes, I do. Good. So what we can do is, okay, so we saw this, right? This is definitely going to be greater than this. Are you sure about this? Like, definitely, because r is always greater than any of the r's you take, greater than or equal to at least.
Yeah.
Makes sense? Yeah. So what we can say for sure is that the pressure at center is greater than this 0 to m integral gm by 4 pi r power 4 times dm. Cool. Now is greater than gm square pi. Does this make sense? So what we've got is a certain lower bound, a sort of least amount of how much pressure can be at the center of a star of a certain mass and a certain radius. This is actually kind of good because although this might seem a little, I mean, it's you never know what the pressure can be, but then now we're defining the lower bound. But that's basically all we can do with how much data we've got now, because we don't know how anything varies with anything else. It's kind of, I wouldn't say this is very inaccurate though. I mean, for the sun, you get something like 10 power 13, while whatever your actual answer for your actual quantity or your actual sum for pressure at the center is 10 power 15. It's changed about the order of 10 power 2, but that's fine. There's a good lower bound. Quite a nice thing you've got. Because with this, we'll be actually able to somehow get what the least temperature at the center should be. Now that's what we go to next. Temperature at the center. We know the pressure, or at least we know how much the pressure should definitely be for the thing to be a star. That's what we know. From this, we need to go to how hot the star is. And for that, we need something known as an equation of a state, which just relates to two states. And the ideal gas law happens to be a good approximation for this. And why does this happen is because at that, I mean, for sure, we know that it's very high temperature. And at that high temperature, it's actually plasma inside. And all the thermal energy, whatever is in the star, it is enough to dominate over whatever other interaction is possible between the particles in the star. So how do you define an ideal gas? Particles don't interact. Here also, the particles are so energetic that they don't really interact that much. So the ideal gas law is actually quite a good approximation. This is the ideal gas law. The problem is, this is a general equation we're trying to derive. So I don't really know the volume and the number of particles and stuff correctly for that matter. And extensive variables are a bad idea when you're trying to come up with a good generalization. So we try to make it intensive. For that, we define something known as the mean molecular weight. This mu is the mean molecular weight. And this is basically, if for a gas of mass m and n particles, you take the mass by n times 1 by mass of proton, because, well, you for particle, you're considering it to be having how many ever protons it has, because the electrons are way too tiny when compared to the proton itself and then to the star. So that's nothing to worry about. And this is the density if we're considering the density of the gas in consideration. Here's where we need to make a very unrealistic assumption. I might sound like an absolute hypocrite. I might sound pretty dumb when I say that I'm going to now assume that the density is constant throughout, when I clearly mentioned in the previous part that the density is not constant throughout, because that's where we were stuck. Now I'm just saying that we take an average density, which is literally just 3m by 4 pi r cube. And this is basically, okay, no, I'm sorry, this is r cube. Yeah. So this is average density throughout the whole star. We average it and we plug in that into this row here. And we plug in the rest of the values we get. And we get a certain TC. Okay, I might sound, you might be cursing me at this point, but that's fine. And let's just put some values for the sun. And what we get for the sun, I'm talking in specific about the sun, I get this. But what the actual value is this, both in Kelvin. That's actually a good approximation now that you see it, even though I'm taking it to be constant. Of the order of 10 power 1 is usually ignored. So pardon me, but this is what we'll be doing. Right, so when we proceed, we're just basically playing around with the equations at this point. So you see how we took mass to be the variable here, right? We're continuing with the same thing. Mass as independent variable, and this is what we get. So multiply both sides with 4 pi r cube. Don't ask me why. I also don't know why. But you do this. A good answer for why would be because we want to somehow get gravitational potential energy into the picture. So once you do this, we get this. And this is exactly what gravitational potential energy is. So we define this term as omega, this specific term as omega. Put this in. Either, if you have the patience, please integrate it. We'll get something. If not, Wolfram alpha, let's go. You'll get something. It's basically integration by parts, not that hard also. But then, yeah, you get something. You get a nice equation. I don't want to put that set of calculations here. And when you play around with those equations and simplify more, what you get is exactly this. So what you've got here is omega equals -3 times center to surface, C2 as center to surface, pressure times dV. All right, so now what we can do is try getting thermal energy somehow into the picture. We somehow got our gravitational energy into the picture. So what we did then was pressure with gravitational force. Now what we're doing is pressure and gravitational energy. With this pressure and volume, somehow we want thermal energy in the picture. How we would do that is we can take this thing. This is internal energy per unit volume. I think we would have all done this at some point in thermodynamics. When we learned thermodynamics, I think we did this. This is degrees of freedom, and this is number of particles, and this is number density. I'm sorry, did I say number of particles? No, this is the number density, and this is the internal energy per unit volume. Using this, if we go ahead, what we get is, I think I have an empty slide here. Yeah. So what we can get is pressure is internal energy per unit volume times gamma minus 1, where gamma is the adiabatic constant, the ratio between Cp and Cv. Put this thing back in the same in the equation we got here, like in this. This is the virial theorem equation. Now, when we plug this P in there, what we get in the end is this. This is capital U, and this is the total internal energy, was 0. You see what's the beauty here of this equation is that we have very nicely related the gravitational potential energy and the thermal internal energy of the star as a whole. Now, what things get interesting after this. Things get really interesting after this. So what you can say is, this is quite a good. Okay, 1 second. I do not know how to put this across, but you can say that the total energy is the sum of gravitational potential energy, the thermal energy, and a certain nuclear fusion energy. I'll just put that as NF. This thing is actually lost due to radiation. That will come up later again. You see how these have to sum up to 0 with a certain relation here. And that's your total energy. And this has got to be conserved. The best part now is, a star has what we would call a negative heat capacity. Now, this might make you question things more. But yes, we do have what we would call a negative heat capacity. A heat capacity is usually defined as a change in temperature with respect to how much energy you're giving it. So what happens in a star is that you give it energy, it'll cool down. You take away energy, it's going to heat up. Now that is actually quite consistent with this, because if the so what we can say is that we can take a monoatomic gas for this and actually substitute and get a certain a value for this, and you put that in here. Ignore this for now, just put that in here, and you would get that your total energy is less than 0. So it's gravitationally bound all the time. The star is gravitationally bound all the time. With that information and that, what would happen now is, with this information, you can say that E is equal to omega plus U. For now, this we would be considering this later. Please bear with me until then. So this is now, if you make any changes to this, like let's say energy increases, so we can say that's gravitationally bound. So let's consider gravitation first. This increases, and now U has got to decrease. Are you able to wrap your brains around this? I hope. A good intuitive explanation would be that if you give it energy, it expands, overcoming the force of gravitation, so it ends up cooling down. Does that make sense? This is with respect to external energy. I hope it makes sense. So, note, there's always supply and radiation of energy, and that's where we'll be considering this nuclear radiation part, and that'll be coming up in a while. The best part of this now is, if let's say by any somehow the source of energy in a star is at a greater rate, so you're getting energy at a greater rate than it's radiating out energy, and when that happens, what happens? The source of a star's nuclear energy is any nuclear energy for that matter is very, very sensitive to temperature. So when a star cools down, it immediately stops the nuclear fusion. So the rate of production of energy also slows down. And if somehow the radiation is more than the source, the star heats up and makes sure that there is enough fusion, so the star gets back its earlier rate of production of energy. So this sort of nice self-regulation is a consequence of the negative heat capacity and the energy conservation we saw just a few minutes back. Now this kind of ensures that a star exists without exhausting its without not fusing its core anymore. I won't use the term core because you've not seen what a core is yet, but you get the point. Right, so why we ignored the nuclear fusion energy from then is because a star is considered to usually be in thermal equilibrium. Although there are slight deviations, but it quite generally is understood, or more than understood, I would say that it obeys that it's in thermal equilibrium. So what happens is, how much of our energy that's produced in the center where there's fusion happening, active fusion happening, the same amount of energy is radiated at the surface. And this happens quite... So as this happens, you can actually... Do you realize how you can ignore how much is produced in the surface because that much is radiated out? So what you can say is that the rate of... Okay, this is luminosity in the end. This is production and this is radiation. Now this is 0 because how much of it is produced is radiated out. So because we were able to define this in the previous section, we can now say this is 0 from here. So what we can see is, what we can see is if okay, so we actually even related u and omega from the virial equation, right? So for a monoatomic gas, you actually get u to be minus omega by 2. You can try it by substituting the appropriate values of gamma in that equation. So if omega dot, or the rate of change, okay, how to explain this? The rate of loss of gravitational energy is 0, then the rate of production of thermal energy is also going to be, it's somehow going to nullify whatever happens here. So what you get is that in the end. So now what we can say is that there can never be global expansion or contraction of a star. A star as a whole can not expand or contract under its own energy, because whatever is being produced is being lost, and the rest is an interplay among itself. So if it expands, it cools, and so there's going to be contraction of some part, and if it contracts, if it collapses under its own gravity, there's going to be heating of some other part and expansion there. So there's going to be some, if some part expands, some other part will contract, and if some part heats up, some other part's going to cool down. So this is why there can never be global expansion or contraction or heating or cooling of a star in the end. It's all going to be very localized. Like in each layer something can happen, but as a whole, if one layer something happens, the other opposite has to happen in another layer to ensure that it's in thermal equilibrium, which it actually is in. So that's that. And a continuation would be that we are conserving energy everywhere, almost everywhere. So what we can quite without ambiguity say is that when stars radiate out energy, there's got to be something that's got to compensate for that, and that is the source. It can be either the gravitational energy or the nuclear energy, but what we see is that it's nuclear. There was some hypothesis done and it was disproved, but I'm not going there right now. So inside the star, the net energy flux through each layer would be equal to whatever is produced within the layer, if that makes sense. So each time whatever goes out of the layer is how much is produced in the layer. That's exactly what it means. That's pretty much all what it means. All this is to avoid thermal instability, which definitely happens, but not in the static scale we are considering right now. So what we can see is luminosity. Okay, wait. Luminosity is basically energy flux with respect to time. Energy, how much energy is radiated. It depends on whether it's radiation or if it's luminosity, some other luminosity, but then it's basically energy per unit time. So what we can see is whatever goes, okay, again, the R plus dr approach, whatever goes out minus whatever is produced here is how much is actually within the layer. Okay, this is how, again, a little weird to think of it intuitively, but what happens is this is the luminosity that is being given out, and this, okay, wait, give me a second, let me put it in better words. All right, so dl is how much ever luminosity that layer has, that dm amount of star has to give out. So this is how much ever luminosity this layer is giving out. This dm is how much ever mass is in that much of the layer. We define a term epsilon to be how much energy is produced within the layer. This, we can come to this later. Let's just call this epsilon for now. And epsilon, it depends on the conditions of the star and what the star is consisted of. Remember when someone in the beginning said the structure depends on the composition of the star? This is the term that actually takes into account the composition of the star. So epsilon is a very complex looking term, which is a function of the density, the temperature, and now this is a mathematical representation of whatever the star is composed of. I'll just put this as composition. So what we can look at epsilon, when you look at epsilon, it is the energy per unit time per unit mass that is produced within that layer times the mass of this layer gives you how much is going to go out of the layer. So nicely we are able to look at how much whatever goes out is being produced inside. So that's energy conservation. That's pretty much it. So this is your equation of energy conservation. This dm, just get it from the first equation we got, put that here, and there you go. This is your third equation of stellar structure. And the summary of this is basically how much ever goes out is whatever is made inside. Right, we spoke about the energy going out. So whatever is made at the center has somehow got to go to the surface and then be radiated out of the surface. Now, how does it go, and what makes this is basically energy transport? How does whatever is made inside go outside? So that's how is it being transported. Now, for this, something nice is we know how in whatever systems we can observe, there's conduction, convection, and radiation. The major mechanism in stars is radiation. There is conduction and convection, but there convection is major in case of something in case of when you get a high temperature gradient within the star. Temperature gradient being similar to whatever we said about pressure gradient, where it's how the temperature decreases as we go out. Decreases. I won't say anything about decrease or increase, but it's how the temperature varies as we go out. That's when the temperature gradient is high. I'll put this at TGR is high. Convection actually dominates. The next talks on stellar evolution are going to take this into account. They'll go into this in much more detail. And then conduction happens in stars with really high density, like white dwarfs. That's where conduction is more apparent. But usually, in most stars, radiation is what we'll be looking at. Mainly radiation is what we'll be looking at. Right, so, okay, so these are some equations. Before that, F here is now, let's consider a beam, a sort of photon beam of intensity F. F is intensity. Now I take this photon beam of intensity F through a certain layer of thickness dr. Now L is the mean free path. Of the photon. I'm sorry if I say proton. It's the photon. What happens now is you can actually look at this. The probability of a photon being absorbed by the layer is dr by L. Does that make sense? Like, this is the probability of the photon not passing through L. So it's found at dr, which means the photon has been absorbed in dr. So this is now a quantity. It's the probability of how much we can lose in a layer. So the change in intensity as we pass through a layer is the initial intensity times whatever the probability is that the layer absorbs it. So that's what this equation tells us. We define a new term called kappa to be 1 by rho times L, mean free path. Okay. Now kappa is opacity. This is what we call as opacity. Opacity in layman terms is blocking light. An opaque thing blocks light. And that's exactly what it is. It absorbs the photons, thereby not letting the light to pass through. So a lesser mean free path will mean an object, the layer is going to have a greater opacity, which means it's going to absorb photons much more easier. From this, we get that 1 by L equals kappa rho. And you put that in this equation, and this is what you get. We now define a new term, radiative luminosity. This has really high scope of getting confused between notation. This L is luminosity and not the mean free path anymore. This L is mean free path. It's kind of confusing, but that's that. You take this, plug that in here, and what you get is going to be dF equals minus kappa rho. F itself is L rad divided by 4 pi r square times dr. You get this. Keep this as it is for now. All we wanted to know about is the opacity and how it affects the intensity of whatever passes through. So you can actually get a good gradient of intensity as we go out. Again, is negative, so something is getting absorbed, but that's compensated by the radiative luminosity. But then, well, this equation just exists for now. We won't be using it anywhere soon. Let's just proceed. I do not want to confuse myself and anyone else anymore. Now, this is this is energy, this is momentum, this is velocity at light because we're considering photons. Now, this is quite obvious. I think we would have done this at some point when we did our electromagnetic waves and stuff. So you take this per unit time per unit area on both sides, like energy equals momentum times velocity. Energy per unit time per unit area equals gain in momentum per unit time per area. That will just be force per unit time force per unit area. So when you use all those in intensity, you're basically just relating intensity with energy. Where energy absorbed per unit time is luminosity, that per unit area is going to be intensity. And that's where you get the dF term from. The C is from here, and this is momentum. Momentum per unit time is force per unit area because we did per unit area on both sides. You're considering it to be per unit area. You get this. Now, this is what is the radiation pressure, which we did not consider in equation 2 because it was going to come somewhere here. So this is the radiation pressure, which is pretty significant in defining our next equation. So radiation pressure is defined as 1 by 3A into temperature per 4. This is temperature at that instant. A is a constant. I am not getting to how we are going to derive this, but it's quite common. You can find it online also, or maybe sometime later, but not right now. We're not going to derive that now, but that exists. Differentiate that on both sides, and this is what you get. Plug this into this equation, and this is what we get. After complete manipulation using this equation too, we get dF to be this, and then we get dP to be this. Now we relate this from this equation, and we get this extreme fancy looking, extremely complicated looking equation. dt by dr is minus 3 kappa rho L radiation divided by 16 pi AC. This is small c dl r square t cube. Now, yeah, this is our fourth equation of stellar structure, and this tells us about the change in temperature gradient. The change in temperature, rather, the temperature gradient. Remember when I mentioned that there's temperature gradient that affects whether some star is going to be conductive, convective, or radiative? This is exactly that temperature gradient that we need to look at. This kappa is something, again, very similar to epsilon from what we saw in the third equation. Kappa also depends on the material, on the constituents of the star. So kappa itself, again, is a function of density, again, temperature, and composition. And the value of kappa, rather the entire term of kappa, is it varies whether if it's radiation, convection, or conduction. Like you get for each of these processes, depending on the temperature gradient, your value of kappa will change. So this is a fourth equation of stellar structure. Now, what we got so far is how mass changes with respect to radius. We got this. Then we got this. Then we got this, where L is luminosity. And then we got this. So you see how we are still considering only change with respect to radius from within to the surface. And we're proceeding with that. And we got equations for each of these. But now we have 4 equations, sure. Can someone tell me how many unknowns we have for this? This has rho. This one has... These equations are supposed to be having a lot of unknowns. And here you have epsilon, here you have kappa. And the unknowns itself as such, like we know how something varies with respect to something else, but we have no idea how these vary with respect to any of these quantities here, with respect to any of the known, I'm putting known within quotes, quantities. So in the end, what we get is that we have 4 equations, but other than like the main unknowns we have here, we have additional unknowns. So in the end, we have 4 equations and about 7 unknowns. We have 4 equations and 7 unknowns. And you have temperature. You have a lot of unknowns. You can actually look back. We can go back to every equation and look at the unknowns. But then I think by now we do know that we have a lot of unknowns. There's no way to solve this unless we further get to any of these. What we can do is we can find an expression for this. We can find an expression for this. We can try getting another equation of state that will somehow let us connect these 4 equations with each other. So somehow we can, you see how each equation is derived from each other, right? It's not like we can, doing some jugglery with the existing equations without an equation of state is just going to make one equation in terms of another equation. And that's not what we want. We want quite a comprehensive conclusion, comprehensive data to actually tell us how a star looks, despite knowing that there are some quantities that do affect how a star is going to look. So what happens is you end up getting, this will involve a lot of statistical mechanics. I don't know enough to go into much detail about that. So what we can say is that there is going to be a certain equation of state that's going to relate all these. And we have very computationally intensive quantities that is going to get us to, you saw how each of these has a matrix involved with them. And then we're going to get some, you have a lot of terms that you'll be considering, from something known as an equation of state table, where it's not one equation of state, it's a table of a lot of equation of states, and how each of these equations are going to play with each of those equations of state. You see how intensive it gets computationally as we proceed. This is not anymore PV is equal to NKT. So there's there are random things you get, like you get something like this. I don't want to go into this now, but then yeah, you get something like ln rho at constant, considering these to be constant. Now you have like multiple terms like this coming up. They're extremely complex. I don't think I'll be able to finish any of those within the time of the talk. But using all these, what we can quite accurately to a certain extent predict is whether the star is going to be radiative, conductive, or convective, how much of energy is made in the center and how much is going out. We can get a good estimate about a better estimate about what pressure and temperature are at the center. And we can talk about how much pressure is, how dense the star is in the center over the surface. And we can talk about how each layer gets less and less massive as it reaches the surface. once we are sure of how much each of these changed from the beginning, we'll now be able to, with of course these assumptions intact, we'll now be able to, in a certain sense, be able to predict the internal structure of the star as such, with all the densities and all the variables you had told me about in the beginning. Predictions about the luminosity is exactly what we did in the third equation of stellar structure. The colors, and we can relate the temperature to the wavelength and get the colors. And the further evolution can be considered from whatever the temperature gradient and how, if convection dominates or if conduction dominates, where it goes. And all these aspects and how the star is going to evolve. With this much data, or I wouldn't say data, with the knowledge of these.
Harini,
Yeah.
just to like confirm, like how much
Yes,
is it left? Like we are well past.
Not much. I think we're almost done. Yeah, we're almost done. About like 2 minutes
cool.
more. Yeah.
Okay, cool.
Yeah, I would not be going into any more detail about any of these things. Just know that hence, after this, it's a lot of statistical mechanics, and I do not know enough to be able to honestly convey it in a good way. So we can stop at this and say that once we're through with the other equations of state and the when the unknown variables of epsilon and kappa are concluded from other sources and equations, we can make quite a comprehensive model, a stellar structure model, which will now enable us to somehow predict what happens further. And that is going to be the next few sessions on what happens after this. And I will stop now. I think that should be fine. It was must have been very, very intensive, but yeah, I'll stop at that. I don't think we'll be going further today. I hope that was not very confusing.
No, I personally liked it. Like the way you explain by writing everything, like it's very nice.
Thank you.
Okay.
Thank you so much.
Yeah,
Any questions?
guys, anyone, if you want to add anything, if you want to ask any kind of questions, feel free to unmute and ask. Yeah, sure, you can.
Someone raised a hand.
Yeah, GBRK. Yeah.
Go on. Yeah.
You said a star can never undergo global expansion, but in the case of B phenomenon,
in the case of what phenomenon?
B phenomenon, B
Okay,
emission phenomenon.
Right, go on.
Like in the case of emission-like stars,
Mm-hmm,
they form a decretion disk from the gas that is present on their photosphere or the outer atmosphere.
Exactly,
and
exactly.
It's a transient phenomenon.
Mm-hmm. Right, so
And
you're talking
we also have mass loss from evolved stars.
Right. Mm-hmm.
It's a function of their metallicity and so on. Which, like all those unknowns you said, kappa and that is
Right, kappa and
so
epsilon, yeah. Mm-hmm.
So, but this equation states otherwise, that a star can never undergo global expansion. Can you comment about this discrepancy?
Right, so it's a very good question actually. Yeah. What I meant by not be okay, so the data you got about the B phenomenon is from above the photosphere, if I'm not wrong, right?
Yes, it's from the photosphere and around
from the photosphere and after that, right?
It's a decretion disk.
So what happens, what the equation we just derived stated is that if from one layer onwards, if something happens, something else has got to happen within that, like inside of that, to counter that. So if you take a certain layer X and say that from X above, I see expansion everywhere, you would be seeing contraction somewhere X below. Does that make sense?
I was talking about in the case of the final days of a star, like the outer layer, outer layers, that is the outer envelopes expand and the inner core strings. I'm talking about that sort of.
That is the most apparent part of this phenomenon is there. Like, well, again, like we said, at this point we're just considering a time scale that is static. So we are not really looking at extreme, very, very apparent expansion. So considering the static aspect, this is right. at least this is what we derived from what made sense on the paper. So if we could, like you said, in like the end stages of a star, when the core shrinks and the envelope expands, that is again a consequence of the same equation. I mean, it's just the most apparent. I mean, you can see it happen. I'm not sure if you could see, if you can sense the contraction, if you can pick and point that this is where contraction is happening from when the phenomenon we were talking about happened. But definitely it's very, very apparent in the end stages of a star. And also the fact that we're considering a star to be static at this point, if you don't look at the end stages as such, you can again say that if something happens at some layer, some other layer, something else has got to happen to cancel out whatever happened in the beginning. I'm not sure if that was clear enough, but once stellar evolution and seismology sessions happen, I think your answer will be more clear. You'll get more clear.
Okay. And why haven't you included gravitational radiation from the stars?
I'm pretty sure. Okay, all right. That's a good question. Gravitational radiation has got to do. I'm actually not sure why I've not considered that, because when I studied this, I did it under the assumption that gravitational radiation is much lesser when you're considering pressure from radiation or nuclear radiation, and then there's heat. So
actually, you're correct. It's quite negligible for stars.
For stars, right? Mm-hmm, mm-hmm.
Yeah, in comparison to black holes, it is negligible.
Right, that makes sense. That actually makes sense. I mean, maybe it would have made sense in the beginning of when a star forms, when it's still collapsing. It probably makes sense at that time. But when a star is existing as a star, so what you said probably makes sense. I mean, it should make sense. At least that's the assumption under which I studied the topic. So, yep.
I have a question on the same note, like about radiation only. You said that in case of like we are ignoring the convection radiation because temperature gradient is not enough. But like
we are not. Yeah, go on. Mm-hmm.
Yeah, so like in case of temperature gradient, like if you're talking about, is this the temperature gradient between the core of the star and the surface?
It is, yes. It's the equation for temperature gradient throughout.
Yeah,
and
so like,
the kappa varies. So what you said about whether I'm not ignoring convection or conduction. It's just that kappa is not the same kappa for each case. So if you're considering convection, you're going to have a different kappa, and if you're considering radiation, you're going to have a different kappa, and if you're considering conduction, your equation itself is slightly different.
Okay, so in case of opacity, like kappa, if you're talking about, is there any range for like different types of stars? Like,
there should be a good range. There is an estimate. There is an estimate about the temperature gradient and the difference in temperature gradient that determines what class a star falls into, but that will definitely come up in the next lecture, in the next discussion. That's definitely going to come up in the next discussion about a certain minimum beyond which there's got to be a temperature gradient different, lesser or greater than a certain minimum. Is that what you're asking? Like something like how in fluid dynamics you have the Reynolds number and then the turbulence, something like that, right?
Kind of,
yeah. It's on those lines. There's definitely going to be a detailed explanation in the stellar evolution part. So.
Yeah. Okay. So like in that case, so even if we are talking about convection, if we want to consider, so all these things we need to, like kappa and all will change, so we will have to have the
yes, precisely.
Okay.
You're right. Yeah, someone raise a hand.
Yeah.
You said that the surface of the star, the pressure is 0, but nothing is cooling down. But if you consider the star's magnetosphere or the magnetic fields, they do exert pressure.
That's very negligible. The magnetosphere and the magnetic field of the star, the distortion, like the whatever effect it produces, is in the order of 10 power 1.
d square by 8 pi, that's pressure.
Sorry?
d square by 8 pi, I'm talking about that pressure.
Alright, just give me a second. Let me that would still, whatever, even after considering the magnetic effects, it would still be negligible enough for us to not consider. In fact, even here, we're actually, in a certain sense, ignoring the radiation pressure itself. What I meant there was with respect to only gas pressure in the dominance. So magnetic pressure due to magnetism is much lesser than radiation pressure itself in a star. So when I'm not considering radiation pressure also there because of the slight, because of, well, it's different in the order of magnitude is much lesser compared to whatever I was looking at there. So someone say something?
I guess it was a disturbance.
Okay. So you just end up ignoring even the magnetic effects. In fact, that way we can even talk about how the there is, if we start considering magnetic effects at every stage, it's going to get a lot more complicated, and I don't think we can do anything with just 4 equations of structure and 1 equation of state for that matter, right?
Okay. Is there a general equation encompassing all these effects?
Which equation?
Is there a general equation?
Isn't there a general equation? Is that what your question is?
No, is there a general equation? There is at
These
least
4 equations are made under way too many assumptions for almost every star. So these 4 equations hold for very general. These 4 are like the very as general as you can get.
Okay.
And even add specifications depending on like the type of star and the whether it's a binary and whether it's close to a black hole or not. And it really depends on. Then again, we consider isolation, and that's the point. Is like we assumed way too much. For most, the more we get into the specifications, we'll just be cutting off the assumptions one by one, and we'll get to a more conclusive, more comprehensive model. And definitely, it's yes, that happens, but that's a lot more complicated than the scope of my information at this point. So.
Okay, I get it.
You get it, right?
Thank you.
No problem. You're welcome.
So are there any other questions if anyone wants to ask? Otherwise, we will wrap. Okay, so if there are no questions, basically this was the first talk of our series, this mini series, I would say, and I would say like it was really a nice one. I pretty much liked it. So I guess everyone liked it. And for the second talk, we will send out a mail again. So please join that talk. So let's see. So yeah, thanks a lot, Harini, again. For such a wonderful talk.
Thank you so much for the opportunity. I enjoyed preparing for the talks. Thank you.
Yeah. Okay, then we will wrap up the meeting. Thanks everyone for joining. Yeah.
Before ending the meeting, could you just show the references slide? I'll just grab a slide.
Sure. Sure. 1 second. I'm still presenting the slides, right?
Yes.
Yeah. It's not in full, but
You can look at the last this link. I think I'll just put it on the chat box. 1 second. The first reference is like it's part of the lectures I attended, so I'm not sure if the resources is that resource is accessible. I'm not sure if that's a public resource. The second is literally just a Wikipedia because I looked up the definition of a star, and well, yeah. The third is pretty similar to the first set of references. So yeah, that the last. You can check out that PDF I just sent. It's pretty good.
Okay, thank you.
You're welcome.
Okay, then if there's nothing else, we can wrap up. Thanks a lot, everyone, for joining. Thanks again, Harini.
Thank you so much. No problem.
Yeah.
Thanks a lot. Thank you. I hope it was informative.
Yeah, it was. Yeah. Okay.
Thank you then. Thank you.
Yeah. Bye-bye.